Hello there, this is an Algebra 2 video. It is Chapter 6, Section 4, and today we are talking about nth roots. Now the nth root of a number, before we get going here, I want to give you some examples. We talked about square roots in the last lesson, but here we're going to go on to roots that go beyond square roots, cubed roots, fourth roots, fifth roots. So what is the nth root of a number? By definition, the nth root of a number is the inverse of raising a number to the nth power. So I have some examples for you so you can kind of understand what's going on here. For example, here we have some equations on this side. It's kind of like a table. X cubed equals 64. X to the fourth equals 625. X to the fifth equals 32. And then we have a generic a to the nth power equals b. Now we know that a square root, for example, we know that the square root of 4 is 2 because 2 squared is 4. So in a similar fashion, we're looking for a number that raised to the third power would equal 64. So that number would be 4. 4 to the third power is 64. In the second case, 5 to the fourth power is 625. 2 to the fifth power is 32. And then here you would have a to the nth power would equal whatever b was. So this just represents, for example, in this case, you have 2 times 2 times 2 times 2 times 2, 5 times. 5 times 5 times 5 times 5, 4 times. 4 times 4 times 4, 4 cubed. And in this case, whatever n is a generic number. So if n was 7, you have a times a times a times a times a times a times a would equal whatever b was. But notice that in this case, the input that goes in, the x value, is 4, and the output is 64. So when we talk about inverses like we have in the past, that's when you invert the x and y, right? So you'll notice that the cubed root of 64 is then 4. So the output of this expression ends up being the input of this expression, and the input of this expression ends up being the output. So that therefore that whole inverse idea. So the cubed root of 64 is 4 because 4 to the third power is 64. The fourth root of 625 is 5 because 5 to the fourth power is 625. The fifth root of 32 is 2 because 2 to the fifth power is 32. And so we have the nth root of b would equal a because a to the nth power equals b. All right, so we also want to give you guys some anatomy of nth roots. Like I said before, so far we've been talking about square roots, and I will tell you that whenever the index is not present in the homework, you assume that it's a 2. And we never write square root. We don't write square root with the 2 there. We assume that if there's no number written, that is a square root, so it's assumed. But I want to give you guys kind of the anatomy of a radical. And so what we have here is, of course, the little house. That's the actual radical itself, radical sign, if you will. The number or expression that is inside of the little house is what we refer to as the radicand. And then, of course, the little number that's right here tells us what type of root it is, and that's the little n, and we call that the index. Like I said earlier, if the index is not explicitly written, then we assume that it's a 2, a square root. Otherwise, it'll say a 3 or a 4 or a 5 or any other number. And then we have a principal root. Well, there are some roots, especially those that are even, that actually have more than one root. So when there is more than one real root, and particularly that happens when n is even, so when the index is even, like a square root, a fourth root, a sixth root, something like that, then the principal root refers to the non-negative root. In other words, here's an example. 25, the number 25, has 2 square roots. It's an even root because a square root is a 2, an index of 2, so that's even. So it has 2 square roots because 5 squared is 25, but also negative 5 squared is 25. So it actually has 2 roots. So both of those equal 25. So when they refer to the principal root, we're referring to the 5. Sorry about that, I'm in eraser mode. So 5 being the non-negative root. So of course negative 5 is still a root, but the principal root refers to the positive one. All right, and so then we have just a little chart here that kind of explains how many roots you would have depending on whether the index was even or odd. So again, remember that the n represents the index. So we have, if n is even, and a is the radicand, which is the number underneath the radical, then if a is positive and the n is even, then you're going to have one positive and one negative real root, like the 25 had positive 5 and negative 5. Of course, the positive one being the principal root. So you get plus or minus nth root of a. If a is negative, we've already learned in the past that you can't take the square root of a negative number. You can't take the even root of any negative number. So in this case, you're not going to get any real roots. You'll get imaginary ones, but that's a whole different story. So you won't get any real roots. And then of course, if a is 0, then you get one real root, which is 0, because the even root of 0, the root of anything, sorry, not the root of anything, any root of 0 is going to be 0, whether it's even or odd. So you have that here in the even case, and you also have it in the odd case. You'll have one real 0. Okay? Then you have odd. If the index is odd, then if the number underneath the radical is positive, you're going to get one positive real root, but you're not going to get 2. You're just going to get 1. And then if it's negative, then you do get one negative real root. So for example, the cubed root of 8 is 2, because 2 times 2 times 2 is 8. And in this case, the cubed root, if a was negative, would be negative 2, because negative 2 times negative 2 times negative 2 is negative 8. So in the case of a being positive in the odd scenario, index being odd, you would get one positive real root. If the a value is negative, like this example, you would get one negative real root. And then of course, if you had the odd root of 0, you would just get the one real root, which is 0. Alrighty? So now that that's all taken care of, we want to start simplifying. The lesson is not very long today. We only have 3 examples to go through, but we want to do them carefully so that you understand what is happening here. So, simplifying. What you want to do when you're simplifying, like I said, this one does not say that it's a square root because there's no index written that says 2, but we assume it's a square root because it's not written. Same is true for B and D, but you'll notice that in part C, it's explicitly written as a 5, so this is a 5th root. So our goal is to take the radicand and rewrite it in such a way that it's with powers of 2, because the square root is a 2, and any square root will cancel with a square. So for example, we know that 16 is the same thing as 4 squared. So I'm rewriting the 16 as 4 squared. But we also have to rewrite the variable. Y to the 4th power is not going to cancel with the square root. So we need to rewrite it, and what we do for that is to basically use multiplication to write the variable as a power raised to a power. So we know that when you have a power raised to a power, you multiply the exponents. So 2 times 2 is in fact 4, which is y to the 4th. And so we now have the square root of that. Now anything that has a square root and a square is going to cancel. So we are going to end up, well, don't forget your plus or minus. Because these squares and square roots will cancel. Now it's not going to cancel both of them. It's just going to cancel the one on the outside. So we still have a 4, and we still have the y squared. And that would be our answer, plus or minus 4y squared. Alrighty? And so now basically what we could say is that the square roots of 16y to the 4th are positive 4y squared and negative 4y squared. Alright, so we're going to try again in part B. Same idea. We want to take, we have a negative in this case, so our answer will end up being negative. And so we have a square root again. So again, our goal is to get this entire, by the way, don't try to cancel this square with the square root, because this square is inside of these parentheses, which is being governed by this 8 out here. So what we have to do is convert that 8 to something with a square in it. So I know that 4 times 2 is 8, so I'm going to rewrite that as x squared minus 6 to the 4th power, and then raise that to the 2nd power. So 4 times 2 will give me the 8 that I'm looking for. Then I'm going to draw in my house here. And my square root and my square are going to cancel, so to speak. And what's going to be left is the x squared minus 6 to the 4th power, and of course the negative. And that would be my final answer for part B. So the square root of negative square root x squared minus 6 to the 8th power is negative x squared minus 6 to the 4th power. All right, so now we're going to try one that's a little different, because now instead of squares we have to the 5th power. So now what we want to do is we want to rewrite everything in terms of 5s. Okay, so the first thing we want to do is 243, and I believe that that's a 3, but I'm going to confirm that. 3 to the 5th power is in fact 243. So what I'm going to do is I'm going to take and write 3 to the 5th power. That's the 243. Now a to the 20th I know is 5 times 4. So I'm going to go a to the 4th and then to the 5th power. So that's going to give me 4 times 5 is going to give me the 20. And then we're going to go b to the 5 because 5 times 5 is 25 and I need 25 b's. All right, and then we're going to put our radical back on with the 5th, well, number 5 is the index. And anything that has a 5th power is going to cancel with that 5th root. So we're going to go ahead and cancel all these 5s, kind of like that. And so we're going to end up with 3, a to the 4th, b to the 5th as our final answer for part C. And then we're going to try our last one, which is D. And with D, the first thing we have to notice right away is that we don't have to go anywhere. This guy will not have any real roots. And the reason for that is because this is an even root, which is a square root, right? And you have a negative 16 there. We just talked about that earlier. If the negative 16 is basically throwing everything off. Now this will have imaginary roots, but it won't have real roots. Now if you want to, just for practice, go through and see what that would look like, we can definitely do that. The negative 16 would be negative 4 squared. Actually, it would be negative out here, and then 4 squared. So let's do that, and I write that the right way. It would be negative 4 squared x squared squared, and y to the 4th squared. So what I'm doing is I'm taking all these, x squared is going to be x to the 4th, 4 squared right here, 4 times 2 is going to give you the 8, and so the square root's going to cancel all those. Because this is a negative 4, and the square's going to cancel, you're still going to have negative 4 there. So you're going to end up with an I. So if you remember before, whenever you had the square root of negative 1, you have I in there. So we're going to go, and this negative 1 guy here is I. So we're going to get 4I x squared y to the 4th. So this would be the roots, but like I said, they're not real. Because the I is in there, those roots are not real. So they're imaginary roots. Now they didn't ask us to find imaginary roots. So in the future, when you're doing your homework, if you have a negative radicand for an even root, you can just say that there's no real roots. You don't have to keep solving it. I just wanted to solve it for you so you could see how you would to give you more practice with the canceling and stuff. But you don't have to do that part. If it's going to be imaginary, then don't worry about it. Just put no real roots. So here we go. Your do-it-yourself question only has 2 parts to it. I did 4, but that's okay. And so then we're going to move on to something that's going to be a little bit more specific for us. I want to give you guys a scenario here, if you will. We do have a problem a little sometimes. In the previous example, we didn't apply any absolute value bars because we were assuming that all the variables were positive. But that isn't always the case. And so I want to show you guys this example up here. And I know that it seems kind of weird wordy, but just kind of bear with me here. It says, notice that when x equals 6, then the square root of x squared, and if you replace the x with 6, is going to equal the square root of 6 squared, which we've been canceling, but technically the square root of 6 squared is 36. and the square root of 36 is 6, which equals x. So in other words, at the end of the day, you get the same value that you started with. But what if x is negative 6? And we have the exact same thing. If x was negative 6, then you still have the square root of x squared would equal negative 6 squared, which negative 6 squared is still positive 36, and the square root of 36 is 6. But in this case, 6 is not equal to x. In other words, 6 is not the number you started with. You started with a negative 6. That, my dear fellows, is a problem. So, basically what this means for us is that you have to be careful when you have even roots, because the even roots are the ones where you can't take square roots of negatives. So therefore, whenever you have the nth root of a to the n, so when you're canceling, okay, then that has to equal the absolute value of a. We have to use absolute value bars when n is even to ensure that we keep things positive. The absolute value basically keeps everything positive. So we need to do that whenever that happens. So we're going to show you some examples of how to work with the absolute value bars. And so here we go. In theory, the idea is that because they're both the same index here, the index and the exponent are the same, they would cancel. It's kind of like this situation, nth root of a to the n. But 4 happens to be an even number. So our answer is not just y, it should be the absolute value of y. Okay, so what happened here is, which is what I put over here, you got to be careful. It says you have the even root of an even power, and the result is an odd power. So basically what happened there is that the even root, I had the even root of an even power, and when I canceled it, I ended up with y. Based on what I know from before, my answer was y to the 1 power. Since my result is an odd power, I am forced to put the absolute value bars. This is now my actual answer. Now, unless the problem says that you're assuming that all variables are positive, then you have to put the absolute value bars. If you don't, then it's wrong. Okay? So then here we are over here, same idea, but now we have, this is not a b, I'm sorry if it looks like a b, it's supposed to be a 6. So it's the 6th root of 64 times x squared minus 3 to the 18th power. So we're trying to do the same exact thing we did before. We want to rewrite the 64, and we know that 2 to the 6th power is 64. And with the 64, there's no doubt about whether or not the number is positive or negative. We know that 64 is positive 64. So that's okay, 2 to the 6th. And then we're going to do x squared minus 3. But we're going to do this to the 3 times 6, because 3 times 6 is going to give us 18. So I'm going to rewrite the x squared minus 3 to the 18th power as x squared minus 3 cubed to the 6th power. So now I'm going to write my radical in, 6th root there, and just like before, they're going to cancel. But what's going to happen is you're going to get 2 and then x squared minus 3 to the 3rd power. Okay, so what happened here is you have an even root of an even power, okay? So you had even roots, the 6's, of an even power, and the result is an odd power. The result is 3. So because the result is an odd power, you have to put the absolute value bars. But notice that I'm not going to put them on the 2 because the 2 is already positive. We know that 2 is positive. Now if 2 had been negative for some reason, then we could have done that. But 2 is positive. So when it comes down to the number, you don't have to put the bars on the number, only on the variable expressions when you have an odd power as the result of an even root and an even power canceling. So now this is your final answer. Okay? So hopefully that made sense for you. And now you can try this do-it-yourself question. And then we have one more example, which is more of an application problem. And so it says, and this is referring back to the beginning of the lesson, there's like an introduction example about cyclists and whatnot. But basically, in a nutshell, what they're asking us is if c equals the fifth root of b squared, so we have our radical expression right here. If this equation represents the number of collisions and b represents the number of bicycle riders per intersection, estimate the number of collisions at an intersection that has 1,000 bicycle riders per week. So basically the c represents the number of collisions and b represents the number of bicycle riders. And they're telling us that b is 1,000 bicycle riders. So what's going to happen is, I'm going to try to solve for c. I want to find out how many collisions. So I'm going to get the fifth root of 1,000 squared. Okay? So this is not as complicated as you might think that it could be. So all we have to do is to get rid of the fifth root. Remember that how inverses work. To get rid of the fifth root, all you have to do is raise it to the fifth power, because they're inverses of each other. Okay? So I'm going to get c to the fifth power. So now I'm going to get sorry, that's not what I want to do, because I don't want to solve for, sorry, I just did that backwards. That's actually what we're going to do for part B. But let's do this. We can just use our calculator here. We don't need to do any of that. This is actually the easier one. So to find our answer, it's going to be an estimate because it's not going to go in even. But what we want to do is, what is 1,000 squared? So we're going to go 1,000 to the second power, which is 1,000,000. So what we want is the fifth root of 1,000,000. And this is where things get interesting. I want to show you on your calculator how you can do this. There's a couple of ways that you can do this. You can rewrite the radical as a rational exponent, which would be to write 1,000,000 and raise it to the 1/5 power. Remember that 1/5 is the same thing as the fifth root. But I also want to show that you have a button on your calculator that will do any root. Obviously you have a square root button, but if you go to math, so I'm going to show you the steps here. If you go to the math button on your calculator, you will see that option 5 has next to it an x root, kind of looks like this. It has you'll see the cubed root there, which is option 4, but you also see option 5 is the xth root. Okay? So what you want to do when you want to solve this guy is to go to math first and then 5. So sorry, what you have to do first is you have to enter the root that you want. So if you want the 7th root, you have to type 7 first. If you want the cubed root, you have to type 3 first. If you want the 5th root, you have to type the number 5 first. So I'm going to type in 5, then I'm going to go math and option 5, and now it's going to do the 5th root, and then I'm going to type in 1,000,000 and hit enter. And we can get our answer. You can even type in from here 1,000 squared if you want to. 1, 2, 3, 4, 5, 6. I didn't have enough zeros earlier, sorry. So now your answer is approximately 15.84 or 85. Okay, now that's the number of collisions. So the number of collisions at an intersection. So 15.85, almost 16 collisions at that intersection per week. That's not good. All right? I mean, obviously for the people that are in the collisions. So part B, we're going to go backwards this time. If the total number of collisions reported in 1 week is 21, so this time they're telling us that C is 21. Okay? And they want us to estimate the number of bicycle riders. So we're trying to find B. And this is what I was doing earlier. I was getting ahead of myself there. But this is where we are going to take and raise both sides to the 5th power to get rid of the 5th root. So 21 to the 5th power is a really big number. It is 4084101. And on the right-hand side, we're going to have we're going to have b squared. Because the fifth root and the 5 power out here canceled, so the radical is no longer there. All that's left is b squared. To get rid of b squared, I think we all know how to do that. We take the square root. So now you want to go and find the square root of the 4084101, and then you get that b is approximately 2020.92, or basically 2021 bicycle riders at that intersection. That's a lot of bicycle riders. Okay, so that's how you do that. And so now we have this do-it-yourself question, basically the same idea, different formula, but they want you to solve. In this case, they're giving you the volume. They're telling you what V is, so it's a real simple plug-in kind of problem like it was in the last one. And then in this case, you want to go backwards and find, they're going to give you the surface area, and they want you to find the volume. So they'll give you the S part, and then you have to find the V, so working backwards. But once you have completed this example, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.